Hello, it's Keith here, and this is lesson 24 of the simple series of my 6502 assembly programming tutorials. Now we looked before at how to get a Chibico bitmap onto the screen. That's my mascot, you can see it here, and if I have the window selected and use the right keys, we can move our Chibico around the screen. And this is, although I'm controlling it with cursors today, this is actually joystick control. But before, the Chibico had to stay on the screen. However, this is an upgraded version, and the Chibico can be partially off the screen, and this is known as Sprite Clipping. So what we're doing is we've added to our drawing routine, and it's now checking if the sprite needs to be partially off the screen based on our coordinate position, and removing parts of the sprite accordingly. That's the example we're going to be looking at in today's lesson. So we've upgraded our previous version. The drawing routine is now substantially more complicated, a little bit slower as a byproduct, but this will allow us to crop our sprite if it goes off the screen. So if you're creating a scrolling game, like my Suck Hunt game that I really recently did on the Z80, that was a scrolling shooter, so sprites needed to partially go off screen. So we'll be learning how to do that today. Okay, well, first of all, we're going to have to discuss some theory. So the first thing I want to discuss is the concept of coordinates. Now, in our game coordinates, typically in the past, we had a coordinate system where 0, 0 would be the top left corner of the screen, and that would be if our sprite was all the way up here, and then it would go across and down the screen. So our maximum coordinate would be the maximum byte across the screen and the maximum line down the screen. But now we need to be able to cope with coordinate systems that allow the sprite to be partially off the screen, like maybe somewhere like that. So we need to be able to have some kind of negative coordinates where the sprite is partially off screen. Now, I don't like to work with negatives because it makes coding more difficult, or at least makes me thinking of the coordinates more difficult. So I'm using a coordinate system where the minimum coordinate is 0 and the maximum is still within 1 byte, 255. The reason we work with single bytes is because we're on an 8-bit system, and 8-bit systems are slow in 16 bits. So we want to limit ourselves to bytes. So in my games, I tend to work at 256 by 192 physical screen resolution, because most of the systems that I work with, that is a good all-rounder system. You know, some of them are slightly larger, some of them are slightly smaller, but most of them can work within that as a minimum. You know, so it's the Spectrum, the MSX, the Amstrad CPC's higher, so on and so forth. So I wanted to have a coordinate system, a logical coordinate system that would work well within that resolution, but would allow for an invisible area around the screen where the sprite is entirely off the screen, and that would allow it to be partially off the screen. So what I do is I use a logical coordinate system where the visible screen is 128 by 96 logical units. Now this is the equivalent of 256 by 192, the visible screen, and so each logical unit is 2 by 2 pixels. Now this is in the center of the screen, and so around this there is an invisible area, this gray area here. And so if we positioned our Chibico with the pixel coordinate of here, then this part here, the dark part, would be off the screen, and this light part would be drawn as the visible part of the screen. Now, unfortunately, the Apple II has a rather unusual way of working with its pixels. Each byte of screen memory contains 7 pixels, which does not work well for my usual way of doing things. So it's rather irregular, but each byte of the screen is going to be 4 logical units as we're working today. Now usually that would be 8 pixels, that would work quite well, but on this system it's an irregular 7. But basically it's the most sensible way we can work, and the cropping routine we're looking at today, although it works in logical coordinates that are groups of 2 pixels, the cropping actually only works in single bytes, because anything other than that would be extremely slow, wouldn't really be possible on these systems in a practical way, at least. So we're cropping to bytes anyway. Okay, so let's have a look at the code that we're working with today, which, as always, you can download from my website. So here is the code that we've got for today's example. So we're starting off here, we're defining the logical coordinates of the screen. So we're defining a logical screen that's 160 units wide and 96 units tall. And we're defining the minimum X and Y position as 48, 80. So that is the logical pixel that will be the first visible one on the screen. And the cropping routine will use these to convert a logical position to a physical position, and at the same time it will also recalculate the size of our sprite. let's go over to the blackboard and let's actually discuss that, because that is a rather important topic that we need to also understand. As I say, unfortunately, there is quite a lot of theory involved in today's topic. So if we imagine that that is the screen, and imagine that it looks something like a rectangle and not an awfully drawn scribble, and we've got a sprite, and that's our sprite, and our sprite, whatever shape it is really a box, because we're transferring a rectangular shaped grid of pixels to the screen. Now our sprite will move around the screen, and the previous version did this, but it only allowed it to be completely on the screen. But this version will allow our sprite to be partially off the screen, and we will crop it as required. But how we crop it will depend on where it is. For example, if it goes over the top of the screen, well, what we're going to need to do is we're going to need to skip the top part of the sprite and change the height of the sprite and change the starting drawing position of the sprite to the top of the screen. But if it goes over the bottom of the screen, well, the job is going to be different. In that case, we just need to change the height of the sprite. Well, if it goes over the left side of the screen, well, we need to skip this part of the first drawing. Then we need to change the width to this part. But then after we do each consecutive line of the sprite, we also need to skip this part. Rather complicated. Well, if it goes over this side of the screen, the procedure is different again. We need to change the width again. We need to change the width to this part here, and we need to skip this part here. But we don't need to skip anything before we start drawing. And of course, our sprite can actually go over multiple sides of the screen. The Sprite Clipping routine we're looking at today does allow that. I say that because the Chibi Akamas one didn't work properly. It couldn't do cases where it was over two sides of the screen because my mathematics is terrible and I couldn't get the algorithm working correctly, but I have done today, hopefully. So we've actually improved and we've got a better example today that we're going to have a look at. Okay. So that's the theory. Now, what we're not going to do today is we're not going to discuss joystick routines. We're not going to discuss the mathematical calculations of the screen position so much because we did all of that in the simple series and also setting up the screen and things. We've covered that before in the simple series. So if you don't know how to get a sprite onto the screen, you really shouldn't be worrying about cropping just yet. So that's not going to be what we're going to look at. The first thing we're going to look at today is the draw player routine, which has been upgraded. So we're now loading the address of the source bitmap data into an IY pair. IYH and IYL are two entries in the 0 page, which are the address of the bitmap data, because we might need to remove parts of it. What we're then doing is we are storing the width and the height in logical units of our sprite, and our sprite is 32 logical units wide and 24 tall. So that is the size of our sprite in logical units. We're then going to run a routine called doCrop, and what this will do is it will calculate the new position of our sprite. Now our sprite position is actually in B and C in the 0 page, so those are our X and Y position, and it's going to alter as required the X and Y position, the bitmap source data if we need to skip anything, and also the height and the width of our sprite. So that doCrop is going to do all of that work, and it's going to convert those logical units into physical pixel coordinates, an X position in bytes and a Y position in lines. Now what might happen though is the sprite might be completely off the screen. If our sprite is entirely off the screen, well, there's nothing to draw, so we won't want to continue. So in that case the carry will be set and we'll just return. But otherwise we're going to start drawing our sprite, and we'll have a look at that later on. First of all, we're going to look at the calculations that we're doing to calculate the cropped sprite. Okay, so here is the start of our code. Now during this routine the Y register will be continuously 0, so we'll sometimes use that as a quick source of a 0. We are resetting something called Sprite Clip, and this is used in the case where the sprite is partially off the side of the screen and we need to skip part of the data after each line is drawn. So that is something we will be doing. So just to start though, we're going to assume that we don't need to do that, so we're setting it to 0 here. We're also resetting D and E. Now these are used during the calculations as temporary variables, so we'll start them off as 0 and we'll load them with other values as required. Okay, so first we're going to consider the top of the screen, and we're going to compare our sprite to the top of the screen and see how it needs to be cropped. So the first thing we're doing here is we're loading the Y position, and then what we're doing is we're subtracting the first visible pixel of the screen in the vertical axis. And if this goes below 0, then our sprite is below the first visible pixel, so it's being cropped in some way. So it might be there, it might be completely off the screen, but it isn't completely on the screen in the vertical axis. So we're going to need to do some cropping. If that's not happened, then we're going to skip the next section because we don't need to crop. But what we're doing next is we're negating that, and so what we're doing is we're taking the amount that the sprite has gone off the screen by in the y-axis, and this is going to be the amount we need to remove. We're then comparing that to the height of the sprite, because if the sprite's completely off the screen, then we would be being asked to remove everything, in which case there's nothing left to do. In that case, we jump to the all off screen routine, which sets the carry and returns, because remember the calling routine will give up if the sprite is completely off the screen. Okay, so that's what we're doing there. If the sprite isn't completely off the screen but does need cropping though, we're storing the amount we need to remove, and we're now setting the new Y position to 0, because if the sprite's off the top of the screen, the first pixel that will be drawn vertically is at position 0 in physical units, in lines basically. So we've now calculated the new starting position. We've either set this to 0 or we've just subtracted the minimum logical Y unit. So we're storing that for later, and we're now going to look at the bottom of the sprite. So we're now adding the height of the sprite, and we're now comparing that to the last visible pixel in logical units. And if we are now over the visible height of the screen, then we're obviously partially off the bottom of the screen. We might be down here or something, we might be doing that. So again, in that case, we need to crop the bottom of the sprite. So we're comparing again to the height of the sprite and seeing if we're going to remove the entire sprite. Maybe we're completely off the bottom of the screen. If we're not, then we're going to store the amount that we need to remove from the bottom of the sprite. So at this point, the E entry in the 0 page stores the amount to remove from the top, and the D entry stores the amount to remove from the bottom. And now what we're going to do is we're going to calculate the new height of the sprite. So we're taking the amount to remove from the top, adding the amount to remove from the bottom. If the result is 0, then there's nothing to remove, but otherwise we need to do some removing. So what we're doing here is we're negating that, adding it to the height, and storing the new height, subtracting anything we need to from the top and the bottom. Okay, so that's calculated the height, but it's not dealt with the issue of updating the source bitmap, because if the sprite is at the bottom of the screen, we just need to change the height. But if the sprite is at the top of the screen, well, in this case, we'd need to remove the head of our character, and that's what we're going to do here. So we're taking the amount we need to remove from the top, and if it's not 0, we're storing it in X, which is going to be a counter, and we're then taking the width of the sprite and we're converting this to a number of bytes per logical line, and we're now storing that in ZE here. And what we're going to do is a simple multiplication routine, and we're basically going to multiply the bytes per line by the number of logical lines we need to remove, and we're adding that to IY, effectively moving the starting position of our source bitmap by the amount to remove. Now, this isn't a very efficient multiplication routine, but this will only occur when the sprite is being cropped, and it will only occur once per draw. This isn't the place that's taking up all the CPU power. That's the pixel drawing routine, not the cropping routine, so it's not a priority for this example. Okay, so we've now calculated the new height and the new drawing position of our sprite as required. So we're now going to do the same for the horizontal position. So we're zeroing the two D and E entries. We don't need them anymore for the vertical. We're going to do the same for the horizontal. So that's what we're doing here. Loading the X position, subtracting the first minimum logical X position here, and then seeing if we've gone below 0. So we're basically testing to see if our sprite is somewhere like that. If it's gone below 0, then our sprite is either entirely off the left hand side or just partially off the left hand side. So that's what we're checking for here. And then if it is partially off the left hand side, we are negating it. We're seeing if the amount we need to remove is greater than the entire width of the sprite, in which case again we're entirely off the left hand side of the screen. Otherwise, this is the amount we need to remove from the left. So again, we're setting the drawing position to X equals 0 here, and we're updating the X position here. Okay, so we've cropped the left. We're now doing the same for the right. We're adding the width of the sprite, comparing to the last visible pixel of the screen in logical units, and seeing if we need to crop the right hand side. And if we do, we're storing that in D in the 0 page here. Okay, so we've now got in E the amount to remove from the left, and in D the amount to remove from the right. We add these two together, we convert it to a number of bytes, because if one logical unit needs to be removed but we can't do that because our routine works in bytes, we need to give up. So we're converting it to bytes and seeing if there's anything left to remove. If there is, then whether we're on the left or the right, whether we're here or whether we're here, we need to remove part of the sprite after each line is drawn. So we're storing that in Sprite Clip, which will be used during our drawing routine to skip a number of pixels after each line has been drawn, or a number of bytes rather, after each line has been drawn. Now what we're doing next is we're converting this to a number of logical units again. We're then calculating this as the new width here, and we're storing the new width just here. Again, this could have gone down to 0, in which case we just need to give up. But otherwise we do have something to draw. Now at this point we've calculated the new width, but what we now need to do is calculate if anything needs to be removed from the left, and we need to update the starting byte as required. So what we're doing here is we're taking the amount to remove from the left, we're converting that to a number of bytes, and we're adding it to the IY entry in the 0 page, which is the source bitmap data. So again, if we've got our character here, well, if the character is at the far left, we need to remove the first few pixels from the start of the sprite before we start drawing, and so that's what we're doing here. Now at this point we've calculated all of our cropping, but we're still in logical units, so we need to convert this to bytes and lines, and that's what we're doing here. So we're quartering the position of our sprite, the X position, to convert it from logical units to bytes, and we're quartering the width to convert from logical units to bytes, and then we're doubling the Y position and the height, because one logical unit is 2 physical lines, so we need to convert that. Because we've successfully cropped our sprite and the sprite is at least partially on screen, we're clearing the carry and then we're returning. Okay, so we've successfully cropped our sprite, so now we need to actually draw it to the screen. Well, the first thing we're doing is we're using the get screen pos routine, and this is the same one as in the simple series, and this takes the XY coordinate and converts it to a screen memory address. And then what we're doing next is we're skipping over the next block of code because it's only used after the first iteration, so we'll see that in just a moment. The first time that our code runs, we load the Y register with 0. This is going to be our moving counter as we draw the bytes to the screen. We're then loading the X register with the count of bytes that we need to transfer per line, and we're going to use that as our loop counter. We're loading a byte from IY, which is our bitmap source. We're XORing it with the screen memory, and we're storing it back to the screen memory. EOR, XOR, this is a way that we're inverting the screen, and this is just a simple trick because I need to remove the sprite quickly, and by using XOR we draw it twice, we remove it the second time. Now each time here the offset is Y, so we're offsetting from our bitmap source and our screen destination, and we repeat until we've done all of the bytes of our sprite. Once we've done that, we then decrease our line count, and if there's more lines to draw, we jump back up to sprite next line, which is up here. Now what we're going to do here is we're going to mathematically calculate the next line of our screen memory based on the previous one, and unfortunately on the Apple II it's a little bit complicated. Now I'm certainly not saying that the code I've got here is the best, but it does at least work. So what we're doing here is first we're transferring the Y register to the accumulator. We're adding that to our bitmap source because we were using Y, but that never actually changed the bitmap source, and we need to change the bitmap source before we do the next line. So that's our source data done, and then what we're going to do next is we're going to update our VRAM destination. Now the memory address of the lines is calculated. If we've got our line number from 0 to 192, then the bits of that line number could be split up like this, and each of those parts need to be multiplied by a different amount and then added to make up the VRAM destination. Now when we move down a line, we're basically going to increment this part, and then if that overflows we're going to increment this part, and if that overflows we're going to increment this part. And that's the best way I could work out, at least, to calculate moving down a line. So first of all we're going to effectively add hexadecimal 400 to our VRAM destination. So we're loading the high part and we're adding effectively 4 to that high part here. Now we're then testing to see if that section has overflowed, and if it has, we're going to have to make a correction to compensate for that, and then we're going to update the next part. So that was testing for this part. but we've overflowed, so we're now going to have to update this part. So this part uses 3 bits, and we have to add hexadecimal 80 to the low part, and that's what we're doing here. We're adding, effectively adding hexadecimal 80 here, but if that has carried over from the low byte, we're then updating the high byte here, and if that has overflowed, we're going to have to update the final part. Now, during this sequence, we're loading in from D and E, but we're storing the values back in X and in Y as a sort of temporary value, and we're going to write X and Y back as required into the DE pair of our VRAM destination. So that's what we're doing here. We're updating the second part here in the high byte of B here, but if that's overflowed, if C overflowed and B overflowed, we're now going to have to update the A part, and that means, rather oddly, adding hexadecimal 28 to the low byte again. So that's what we're effectively doing here. We're getting our low part back, and we're adding hexadecimal 28 here, and then we're storing the bytes back to the DE pair here. And that has effectively, rather palaver, but it's effectively updated our VRAM destination without a total recalculation. Now, in the previous example, I just reused the get screen pos routine. You could do that as well, but I think this version is overall more efficient. I'm pretty certain it is, at least in most cases. I think it's only in the worst case scenario where all of those bytes need to be updated. It might be no better, but even then I don't think it's any worse. Now, once we've done that though, we still need to remove any bytes from our source sprite if our source sprite is partially off the side of the screen. I don't know if you remember, but we had that sprite hclip value that we loaded in before, and that's what we're going to do here. If that is 0, then we're just going to skip the next section because we're not cropping our sprite, but if it's not 0, we're adding it to the low part of our bitmap source, and then if that overflows, incrementing the high part. That's updating our sprite for any cropping that's occurred. Then all we do is we repeat with the main routine, transferring the next line of the sprite. Now, of course, you will probably notice that there's an awful lot of this code, and it's quite complicated, you know, all of this cropping and things, all this recalculating the bitmap. Well, if the sprite isn't cropped, it's going to be a waste of processing power. And this might be something you want to consider when you're writing your game. The Chibi Akams game had multiple sprite engines. There was a sprite engine that could do transparency, and there was a sprite engine that could do cropping, and there's a sprite engine that could do neither. And what I did is I switched between these sprite engines depending on the position of the sprite and also the purpose of the sprite. If the sprite didn't need to be transparent, I just used the fast routine. If the sprite wasn't partially off screen, I used the fast routine. And if your sprite's never going to be cropped at all, you wouldn't even want to calculate the cropping really. So it's quite important with these complex slower routines that you might need to design your game accordingly and use different versions depending on what your game requires at that point. Anyway, I hope you've enjoyed this. If you have, like and subscribe. We're going to be coming back to this kind of concept in the future. I've been working on a tile map routine, a software tile map, which will do simple sprites and simple tiles, and I'm hopefully going to use that in a game at some point. So if you want to see more Apple II, please follow along so that you see that. Of course, as always, go to my website, download today's example. I'm sure it's not the best, but it's at least usable. So if you have nothing better, then you're welcome to use it in any kind of games you want, even if somehow they're commercial. Go ahead and use anything you can off my website in that capacity. Anyway, thanks for watching today, and goodbye.